We talk about the stuff from Wednesday, which is the ultimate goal of this, which was solving for time in our exponential equations, okay? So this is where getting those exponential equations written properly is really important, okay? So let's start, and then we'll talk about this stuff at the bottom, which is rewriting and solving again, just as good practice. Those are a little bit more complex, but they're still not terrible. Okay, so let's dive into this, because lots of words, and it's always gets challenging when we put a lot of words in a math problem, right? So we initially invested $2,500 into a bank account with 2.3% APR, compounded monthly. That account now has $4,000 in it. How long did you leave the money in the account, assuming you never withdrew any money from it? Meaning that you just put it in there and you let it be, because it makes. So this is the key. When you see how long, what this tells us is we're solving for t. Good.
So this has nothing to do with what we're talking about right now, but I just had a weird thought. You know that that one lottery thing where you get like $5,000 a week for life or whatever? How would you do that with this? Like you get
That's called an annuity, and it works the same type of way. That's a whole nother level of this. You got to get this down before you can talk about annuities. All right, so how long means that we're going to be solving for t. So what we need to determine is what type of growth is this? And we know it's growth because we started with 2,500 and now we have 4,000. So we kind of got to identify everything here. So we have a compounded monthly. So that means that the equation we need to use is our balance is our initial 1 plus the rate over that n value times the time. And because we know we're going to be solving for t, that's the only thing that's going to be left as a variable. Everything else in this expression is going to have a number placed in there, because that's what we have to be able to solve equations. We have to have numbers for everything except one item. We only know how to solve for one thing at a time. So we go through, we need to go ahead and put all this in. So initial investment of 2,500. So that means your I is 2,500 into a bank account with 2.3% APR. What does APR stand for? Annual percentage rate. And I put that in there because it's a very common term that you'll see real life with credit cards and bank accounts and everything else. But this is the R in this. So the R is 2.3%, which we can't use that mathematically. We have to convert that to a decimal. So that's 0.023. So we took care of the 2,500. We took care of the 2.3%. Now this monthly in our compound interest formula tells us our n. How many months are in a year? There's 12. So that value is 12. And the account now has $4,000. So let's kind of go through and check off what we've got stuff in here for. We'll highlight it in red. So we know the R, we know the N, we know the I, we know T is going to be what we're solving for. So then this last number has to be the balance, because it's what we end up with after that amount of time. So this $4,000 is the balance. And what we need to do to start is we need to take all of this information that we just pulled out of that word problem and write them in the proper places here so we can go through and we can solve this thing. So the balance is 4,000. The initial was 2,500. 1 plus 0.023, because that was our R, over 12. 12t. T still, so we just put numbers in there for everything except for the time. So our goal is to solve for this time that is up there in the exponent, okay? Now, this is not going to come out pretty most likely. So it means that we'll probably just kind of need to leave that as is and plug it into the calculator with that fraction. But since we're going to use Desmos, it shouldn't be too bad. The key with this initial value that you have right here can't be next to your exponential equation, because this part right here inside the parentheses with the power, that's the exponential part. If I have to move this number, this 2500, over here, and then I'll have an exponential that I can write as a logarithm, which gets the time, which will get the power by itself and allow me to solve for it. So let's divide first. So it's 4,000 divided by 25. That's not the window I wanted. That one is. So we need 4,000 divided by, and we got 1.6. As long as that number comes out as something that stops, that you don't have to round, you can use the decimal and make it a whole lot nicer to write down with. So we're going to write down, we're dividing. So we're going to divide both sides by that 2,500 first, which will cause it to cancel there. And we just found out this is 1.6, and it's equal to all of this stuff. Now, let's just be sure that 0.023 divided by 12 plus 1 isn't something we can write down, because I know some of them in our practice were. So let's actually divide that and see what happens. So 0.023 divided by 12. It tells me it could make it a fraction if I wanted it to. But if I'm going to have to write a fraction, why bother worrying about changing the way that it looks just to type in a fraction? So what I'm saying is, when you get a percentage, when you convert it and you do this division by the end that comes out messy, we're just going to leave that parentheses there. And it'll be something when we plug in that log, we'll plug all those operations inside the parentheses with log, and the calculator will do all the hard work for us. There's no need to try to simplify it. So because it doesn't come out as something nice, we're just going to leave it the way that it is. It's 1 plus 0.02312 to the t. So even though this doesn't really look like it, and it's actually kind of backwards, this is a exponential. We have a base, even though the base is something that looks weird. The stuff inside the parentheses is the base. We have a power, and I lost my 12, I'm sorry, 12t. We have a base, we have a power up there equal to a number. So let's write this in logarithmic form. The base, this crazy thing inside the parentheses, is the base of the log. This is 1 plus 0.023 over 12. This goes inside here, and because we know we want to get this exponent by itself. So it's messy looking, trying to preserve the accuracy till the end, but we'll still be fine. So we're going to use, and I'm going to write it the other way so we can put this normally. I'm going to use change of base on that log. It's the log of two things divided. The 1.6 was taller, so it stays up top. The 1 plus 0.023 divided by 12 is down here. What do I need to do to all of that? Because I want to solve it for t, right? So how do I get rid of the 12? I divide it. Now I'm going to use my notation on the sheet to aid me with the calculator. I know that I want to do this operation first. And then I want to do what with that answer? And you would probably never normally write this out as an answer, but you're going to get a number out of this that we're going to write as, this is the number of years that we left this in this account, okay? So I'm going to plug exactly that messiness into the calculator and let the calculator do all the hard work for me to get to the number. So I'm going to make everything inside these parentheses match first. So we have it was the log of 1.6 on the top, right? And we're going to divide that. Just hit the divide key. Log of, it was 1 plus 0.023. Highlight that. We wanted that divided by 12. That's the messy part, right? And it equals that number right there, 2.45. 245.45421116. Now we're not going to round that. And this is where using the answer function is going to be helpful, because we know that all we need to do is take that answer and divide it by 12. So we hit enter, and then we can just type ANS, and it'll bring up the previous answer, divided by 12. And there's our final answer. And this is where we want to round to 2 places, okay? Use the calculator and the technology to aid you in the calculation and preserving accuracy. So 20.45, because that's after it's a 4. So if we come back to our screen and write down our answer, this was 20.45 is what we got out. And what is that? Those are years. So apparently you left this $2,500 in this bank account for 20 and a half years before you got $4,000. Although considering if you had money, you just forgot about it. I don't know how you forget about $2,500, but if you just forgot about it, that it was in a bank account, say it was something somebody gave you and it just sat there, and then, hey, I'd almost doubled my money by forgetting about it. It's worse things could happen, right? You get the math? A lot of this is you've got to go back to those writing exponentials, put all the numbers in the right spot so you can do the division, and then leverage the calculator to do the hard part for you. So let's try these next 2, because these are the ones that I think you'll see more of. We just got to be a little bit cautious. So this says, how long will it take for you to double your initial investment of $1,000 in a savings account with 3.25% APR compounded weekly? So our initial is 1,000. Our R is here, and we're weekly, so we know it's compounded. So we're going to use the same one that we just did. And our initial is 1,000. I'm sorry, I put it in the wrong spot. Our initial is 1,000. 1 plus, I got to take our rate, move the decimal place, so it's 0.0325. You got to write all of that in there. We're compounded weekly, so how many weeks are in a year? That is 52. And then this is going to be 52 times T. So we took care of the 1,000, we took care of the percentage, the weekly, but we're missing something. What's B? That comes from this word, right? We want this to double. So this, what's double what we started with? We started with 1,000. Double of that is 2 times that, which is 2,000. Now, first step with these is still going to be, we've got to move this one over here by dividing. Now, 2,000 divided by 1,000 is always going to be 2. So we're going to come up here and we're going to write this thing in log form. So it's log of the parentheses stuff. I know 0.0325 divided by 52 isn't going to come out as anything I'm going to want to write. Even if it does come out as a decimal that stops, it's probably going to be longer to write the decimal than it's going to be just to type in the fraction. So I'm going to leave this as its base, 1 plus 0.0325 over 52. The 2 goes in here because remember we're solving for the power. So power ends up by itself. So that means I'm going to do two simplifications in once here. I'm going to write this with change of base. I know I want to do that first. So this is log of 2 over the log of 1 plus 0.0325 over 52. And then to get rid of this 52 over here, I'm going to divide this thing, that answer, by 52. And this mess, even though it's messy, the reason I'm not worried about simplifying it is I know I'm going to plug that in the calculator, and the calculator can deal with this as it's written. So there's no need for me to insert another chance for me to make a simple mistake or rounding anything, and just let the calculator do all the hard work. So log of 2, we're going to divide that by the log of 1 plus 0.0325, highlight that number, and then hit divide over 52. And we have that. Again, that's something that I'd have to round. I don't want to worry about rounding that. So I'll hit enter, type in ANS, and then divide that by 52. And there's my final answer, 21.33. So I ended up with 21.33, and these are always, because of the way they're started, years. Be cautious when you practice this to write the units for the answer each time, because I've seen problems on ACT practice that will give you the same number with 4 different units, meaning do you understand the units that should come out versus actually doing the math, okay? Because it's also one of those things, we focus more on the numbers and not on the units. When we dissect the word problem away from the information, we got to go back, put the information back in our answer. All right, one more of these. How long will it take a continuously compounding account with 5.5% APR to triple? And you notice that this has become shorter and shorter each time, right? So let's highlight what we know from this. So we know that this is continuously compounding. We know it's APR. That's all we know from the problem. The other thing that's going to be important, obviously, is this triple. So because it's continuously, that's going to change our problem. I'm sorry, our formula. This is our initial E to the rate times time. That's what the continuously compounding tells me. There's no in value to hunt for that or anything else. It's a different formula. So we want to know how long it'll take for our account to triple. And the only number we're given, well, let's see. How long tells me, let's isolate that. Since it says how long, I know I've got to solve for this again. That means I need a number for R, I need a number for I, and I need a number for B. I have the number for R. The number for R is right here, that 5.5%, which is 0.055. So let's start writing in what we know. We have this. But we don't know what we started with. And we're not even told directly what we ended up with. It could be like part B, though. If I knew what I started with, I could figure out what I ended up with. But this comes down to the relationship between those two numbers. If we want a triple, right? If we start with 100, what do we end up with? 300. If we start with 10, what do we end up with? We start with 1. If we start with 250. Because how did we find that? We always took this number, right, and multiplied it by 3. We always took what we started with and multiplied it by 3. So because we're missing this, and what I'm trying to get at is, it actually doesn't matter. I could use any one of those 4 sets of numbers for this problem. and the time that it takes for it to triple is actually always going to be the same. Because what was our first step every time? We took this initial and we took the balance and we divided it by the initial. So if this is the initial and this is the balance each time, for each one of these problems, what is the balance divided by the initial? So what is 300 divided by 100? 3. What is 30 divided by 10? 3 divided by 1 is also 3. 750 divided by 250 is also, and it's 3 because I want this to triple. If I wanted it to double, what number would I be getting out every time I divide it? We look back here, well, this was a double. We got a 2. That number that's going to happen is going to be the same based on this word, triple, okay? It doesn't matter what you start with because our operations are going to be, well, we're going to have to divide that first. We're always going to get this same result for triple. So you could honestly, the way that this works, the way I say, pick a number if you're not given one for your balance. Usually I think the easiest thing is to start with 1. If you start with 1, we would triple it, we want to get 3. But you could use 10,000 into 30,000. You could use 10 million into 30 million. It's still going to be the same amount of time for that amount to triple. Okay? So that means when we do our division, we're going to divide everything by 1. Our exponential is this. So let's write that in log form. So our log is base E of 3 equals 0.053t. That's our conversion. Log of E should be written as natural log. So it's the natural log of 3. And because it's continuously, it actually becomes easier to solve, right? Is there another log to divide over or anything crazy like that? Nope. All I need to do is divide that 0.053 over. And that will tell me how long this takes to triple. So the natural log of 3 divided by 0.053. So we're going to go ln of 3, and we're going to divide it by 0.053, and we get 20.73. And we're rounding up because after the 2, there's an 8. That turns that into a 3, so 20.73. So this is 20.7. 0.73, and that's years again, right? So the continuously ones are actually a little bit easier to solve, I think, because they're not quite as messy, but it's important to remember that this can be written like that when you go to do it, okay? And then that whole triple double relationship is important because this part C, you talk ACT wise, is where ACT questions tend to lie more often than not because it requires you to understand that relationship as well to solve the problem. This is one of those when you deal with this solving for time exponentially, they start taking more information away and the problems get shorter. It usually means that they're a little bit more difficult and you have to think about them a little bit more. Let's do these practice ones just real fast, okay? And I know we talked about these in the beginning of class, but let's just practice again. So exponential form, 7 to the 3x equals 12. Remember, your power is what's always by itself, and then the little number is called a base because it's the base of the exponent. Same thing, we're going to write this one in log form. We got to write log. Base of the power is the base of the exponent. the power goes by itself. So this 3x goes over here by itself, and then there's only one spot left for 101 to go, and we're good. And we use that a bunch, as you see, rewriting into log form, solve these problems for us and help us get our powers by itself. Let's solve these two before we move on. So this one's the same, but I want to focus in here on this one right here with number 4A. Our initial thought process with this would be to do what? Well, it's in log form, let's write it in exponential. But if you write this thing in exponential, you get 12x minus 4 equals 52. That really doesn't help you much, because you're still going to have to rewrite this as log and do other things. But I want you to think about this. If you're ever given a log with two numbers in it, you can find that value very easily, because you can use change of base here. And now I can find that number, meaning that to solve for x, I just need to take that number that I find when I plug this into Desmos, and to get rid of that 4, add it to the other side. So now I have something that I can plug into the calculator and I can solve for this. They actually did the first step. They didn't give it to us in exponential form. They gave it to us in log already. And if I have two numbers with the log, I should be able to, I can find that number by plugging it in with change of base and just solve. So let's look at what this looks like in here. So was it log of 12? Was it 12 over 52? I've done forgotten. 52 over 12. We'll hit enter. And now we want to take that answer minus 4, add 4 to it. Let me double check my operations. Yep. And I get 5.59, and there's 0 after it, so I'll leave it as 5.59. So the solution here is 5.59. My decimal point is not working well. There it is. With part B, given it an exponential form, we want to take it to the log. And the reason we want to take it to the log is because we want to, our variable falls up here as the exponent. So we need to get it by itself. So this is going to be log, base of the power becomes the base of the log. Exponent ends up by itself, just like we did on the other side. 101's here. And then we're going to use this to solve, meaning I know I can find this number by using change of base. And then all I need to do to that number is divide it by 3 to get x by itself. So we put the divide by 3 after it. And we'll plug that in and we can find x. So log of 101 over log of 16. We get that answer, and we wanted to divide that by 3, and we get 0.554. So it's 0.55. We won't round up. So this is 0.55, and we could take this 0.55, plug it back in, double check that it gets us close to 100. We could do the same thing here if we wrote this in exponential form. If you wanted to check it as you went through, you could plug this 5.59 in here for x. You should get really close to 52 if you wanted to see that you did it right. All right, one more that I want to do with you. We're going to talk about these solving problems, okay? But there's one more type that is a little bit tough. And it's one that looks like this. When you get x and the exponent of both of these. Because, and well, I'm going to erase this. If we go to write this in log form, well, let's say we're going to put this as our base. We get 7, 5 to the 3x plus 3 equals 2x minus 1. Now, the problem is there's an x over here still. And I'm not sure how to deal with all that yet. Okay? So when you get them on both sides, this is where that change of base formula and that change of base method kind of starts failing you a little bit, because the rewriting doesn't help us a lot. So the way that I want to attack this one is the way that we did those previous ones, where I told you if we put log on both sides, it's the same thing. So when you get x on both sides, we're going to do this. And this is going to get messy, but it's going to give us something that we can plug into the calculator at the end. Now, the reason we do this is there's a property that says anytime I take log of a number that has a power like this, I can write that power as a multiplication. So that means this is 2x minus 1 times the log of 7. This is 3x plus 3 times the log of 5. It still looks messy, but what we've just gotten rid of, and what we didn't see when we, what we didn't get rid of when we used change of base, there's no more exponents to this. It's just multiplication, addition, and subtraction. So that means that I can use normal steps of algebra to be able to solve this. So the first part of this, I'm going to distribute, because log of 7 is just a number. I'm going to distribute that to both of these. So I would get 2x times the log of 7 minus 1 times the log of 7. It's like multiplying 5 through it, meaning if you had x minus 2 and it was times 5, you would distribute, you would get 5x minus 10, because this would multiply both of those things. I'm doing the same thing, but the number I'm multiplying by is whatever the log of 7 is. And notice I haven't even looked at it in the calculator because I don't want to round it, and it's not going to be nice. It's a long decimal. It doesn't terminate. So I'm going to just multiply it as that. I know that I could find that number, but I'm not going to bother trying to write it as an exponent. Or I'm sorry, as a decimal. I'm going to do the same thing over here. So this is equal to 3x times the log of 5 plus 3 times the log of 5. Doesn't look like we've made any headway yet, does it? Now let's think about our goal. We want to solve for x. So what do we need by itself on one side of the equal sign, equal symbol? We need somewhere x equals, right? So let's think about this algebraically. There's an x here and there's an x here. I can't have them on both sides, so let's put them on the same side together. And I also don't want any of this other stuff without an x over there, so we're going to move that as well. So what we're going to do is we're going to minus all of this from both sides. Because I don't want it over here, I want it on the left side. And so it'll cancel there. Now I don't want this over here either. I want it over here, because remember, I want to get x by itself, so anything that doesn't have an x in it, I want to get it to the right side of the equation. So I'm going to add this to the other side so it cancels. And let's look at what we have left. Now we can't combine anything with this, because you got to think these are like variables. Unless they match exactly, they don't get combined. So that's log 7, that's log 5. I can't do anything with that. But so what I have is I have 2x log of 7 minus 3x log of 5. And over here I have 3 log of 5 plus, and I'm going to stop writing the 1 in front of this log just so it doesn't get confusing. Now again, it's still pretty messy, right? But I am getting closer because now I at least have the stuff with x on the same side of the equal sign. But I don't want this log stuff with it. I just want x by itself. What do these two terms have in common now? Hint, I highlighted it. They both have an x in common. So the step that makes this work is I can factor out the x from this. If I take the common x away from both of these, what's left? 2 log of 7 minus 3 log of 5, which is a number that I can plug into Desmos calculator and I can find that value. That's still equal to this stuff. We're almost there. So we're going to take this up here. How do I get rid of this expression on the left side? I don't want it on the left side anymore. I want it on the right side because I want x by itself. This is a multiplication. What's the opposite of multiplying? Dividing. So I have to divide all of this out. And it's going to cancel over here and leave me with just x. It's going to appear over here. 2 log 7 minus 3 log of 5. And now what I've just done is I've got the x all by itself, and I have this really crazy looking fraction now. 3 log 5 plus the log of 7, and I want to divide that by 2 log of 7 minus 3 log of 5. But what I've done is I can plug this into the calculator now. And the calculator will give me my final answer. And this is where having this Desmos scientific calculator is going to be mighty handy, because this is a really complicated expression to get plugged into the calculator, but I can make it look exactly like what I have written on the paper in Desmos. So let's see if we can get that plugged in. So 3 log 5 plus log 7. So 3 log of 5 plus the log of 7. Let's keep parentheses around. That's the numerator. I'm going to highlight all of this, hit divide, and let's give me a nice division bar. And now I can type everything else into the denominator. So that was 2 log 7 minus 3 log 5. So this is, down here, 2 log of 7 minus 3 log of 5. That was right, wasn't it? Double check. 2 log 7 minus 3 log 5, 3 log 5. Yep. There's a long ways to get there, okay? But what I'm getting at is we can take these really complex expressions when we work with log. We don't round them before. We don't want to deal with all those crazy decimals, or even if it comes as a fraction. Keep manipulating them algebraically and then plug in the final part straight into the calculator. Let the calculator do all the hard work. So our answer is negative 7.23. Negative 7.23. And what that means is if you plug this number in for x into both of these expressions up here that you started with, you plugged it in here and here, you're going to get relatively the same number answer when you plug that negative 7.23 in for both of them. That's by far the most difficult one, solving for logs, that you will see, I promise.